Welcome, everyone. We're showing most of the results from the meeting, the Acoustics Workshop from this June for the first time at the University of Michigan in Ann Arbor at the Duderstadt Center, which you can see here. We have a lot of material, so
Joe,
yes.
everybody please mute.
Thank you. Okay, we're at the Duderstadt Center, and the University of Michigan was incredibly generous, giving us just wonderful facilities at a very reasonable rate, and that makes it all possible. Just a few pictures. Here's Jim presiding over things from Cambridge. That's Rafael dos Santos and Sean, the makers. Fan and his crew with Tom. And they have a world-class recording studio there, so we had a microphone project, which we're not going to be reporting on. That's Jeff Michael, Ann Arbor recording engineer. There's Luca doing the measurements. And, oops. Okay, so the team, we had Luca and Lonnie Marino doing measurements. We had the makers, Alex, David, Andrea, George, Spencer, Sung Young, Nick, Wataru, and then Raphael playing the violin and testing here and there, and Sean Hardesty too. What we didn't do is any formal psychoacoustic tests, so there's no need to ask, what did the players think, or did it get better or worse? We're really here reporting on the changes to measurements when you do certain things with bridges and soundposts. So this isn't in the soundpost category, but it's an experiment we did there just because it was simple and we had the manpower, and it answers a question makers are frequently asking: what happens if you incrementally increase the height of the bridge rather than adding and removing weight from the top, which affects the tuning? We simply put veneers underneath, and we went from a normal height and increased with 1 millimeter veneers to 3 millimeters above normal. So that would represent about the range one would go, I would think, a 31 millimeter bridge to a 34 millimeter bridge. And the total gain of mass was less than 0.2 grams. And it's at the bottom of the bridge, so it's not likely to affect the tuning at all. And indeed, the tuning remained unaffected. So it seemed like the best way of isolating just bridge height. So we're going to be seeing a lot of graphs like this. This is basically a smoothed out FRF. Can everyone see the bottom of the screen where it explains what it is? I don't on mine, but
yes,
if you
Yes, we see radiation, violin average, and semitones.
Oh, okay. So generally speaking, we take each instrument and do an average for each step of the way. So these are averages across 4 violins for the 4 steps. The black is the lowest bridge, the green is the highest. So we can see pretty much in every range, the radiativity is going up, which is well explained by Jim Woodhouse's bridge model. It's, if anything, going down in the top range. Well, that's because we wouldn't expect much to happen because it's vertical motion that drives that upper hill, and that wouldn't be affected by the height of the bridge. And so from the lowest to the highest, we see, again, averaged over 4 instruments, those levels across the bands. A little bit of a loss at the highest band. Now, what's interesting is, why don't we make our bridges higher if we want more power? Spectacular. Oh, this is not smoothed. So you're seeing that if you see a peak like that, when you're averaging 4 instruments, that's quite significant, and that's a very sensitive, it's a very important area for the ear, I believe, right in the bridge hill area. So the higher bridge seems to be an advantage here, and with the lower notes. But we all know that too much activity in the B1 modes can lead to a wolf note. And in this case, we see the increasing in tendency to have a wolf note, except that we're not looking at admittance. If admittance tracks down there, it should indeed be worse for wolves to have a higher bridge, and I think we know that's the case. So I think that's what kind of practically limits bridge height. Luca, did you have some slides on that experiment?
Yes, I have some slides on the bridge
Okay.
height experiment as well. I think
Okay.
they're going to mirror what you said. So there's a relatively simple increase. So maybe that would be doubling what you just said, I think.
Okay, so I'll just continue then.
I think so.
Oh. Okay, this is an experiment we did just before the workshop. Luca came in and stayed at the shop here, and we went through a bunch of simple things, more to find out which experiments were most interesting. And one that gets a bunch of attention is how thick should a soundpost be? Does it matter? What materials, things like that, and particularly how flexible it is along its length. So what we did was well, first Luca did a control experiment, put the soundpost in, measured, took it out, and then put it back in the same position, measured again. And that would be the black and the red measurements. And you see slight variations in band levels, really a fraction of a dB and maybe a half a decibel in peak heights or a decibel even. But the point is, in all of the graphs that you're going to see from now on, if you're looking at variations that size for individual instruments, we shouldn't take them too seriously. If it's over an average of instruments, we might be able to take it more seriously. So that's the margin of error. So let's look what happens when we take a lathe. Alex did this, and just make a drastic narrowing in the center. And it seems that not a lot happens. A little bit down in the base, but that's not much more than measurement error. Let's take it further. Seems to regain in the base, suggesting it wasn't measurement error. And now we take the ends down to 5 millimeters from 6.3. And again, not a big difference. This is only one violin, but it suggested to us we're not going to get a lot of interesting results from that, and suggests to me that as a maker, a normal post of normal dimensions is fine. There's not a lot of promise in doing other things. We also tried an experiment we didn't show here of changing the materials. We made bridges of the same mass with carbon fiber, wood, and aluminum. And again, we didn't see any difference. So we ignored that question. Now, a lot of these experiments with soundposts are difficult because it's hard to track where the soundpost is, and it's hard to make a lot of posts and fit them all the time. So we developed in the shop here a 3D printed adjustable soundpost with magnetic tracking. Here's Lonnie did these illustrations of how it's put together. Those little dark things are the magnets, and it's held in place so that the swivel top is held to the part underneath by magnetic force and by museum wax, and it gives a nice feel. It doesn't rock around too easily, and it all fits together. We use white ABS, which is a very inexpensive common filament. So really the printing costs for this are probably a dime. There's some work in making the soundposts. So the soundposts have to have holes drilled in the middle, and they all come apart very easily. So you can switch the middle part and thus change the length quickly. The overall mass is a little bit heavier than the traditional one, a gram versus 0.6. It could be shaved down more if we thought it was important. The main thing is we're using pretty much the same thing for all of the instruments. And we made up this little so this lets let the makers adjust the length of the post very accurately and reproducibly. There's a index in the handle there, going down by tenths of a millimeter. So we felt quite confident in reproducing given lengths and across the experiments. So if you put a little magnet on the outside, it kind of magically tracks where the post is on the inside. And what we did was we printed out some millimeter grid paper and stuck it to the top with museum wax. And then the red circle around the magnet is where the outside of the post would be. And it turned out this is quite a reproducible way of finding the and quite accurate way of tracking the post. But there's some, I love this picture of David as sort of a forest of implements, getting the posts in place and looking underneath to see where it is on the back. Okay, so north-south experiment, one of the big experiments. What happens when we move a post from behind the bridge 4 millimeters to 2 millimeters to directly under, and then why not 2 millimeters on the other side of the bridge and then 4 millimeters on the other side? And the measurements we used were just the HV24 radiativity. That's the full radiativity cycle. And so I'm going to break this down into a few different parts. What happens if the post is directly under the bridge? Why don't we do that? Okay, so the black is the normal position, 2 millimeters south. These are all about 1 millimeter on the inside, I think. And then the red is directly under. And we see that something very interesting has happened, which I haven't seen an adjustment that changes the transition hill drastically in frequency and in amplitude. So what we're seeing is a big change there. Is that a pleasant one tonally? In some cases, in no cases, we get a little bit of gain up here and a little bit of loss here. So a little bit of gain in the very high frequencies, a little loss at the bridge hill, a little bit of a gain with the B1 minus. But the impressive thing is this. Now, I'm not looking at all the instruments individually. So these are averages. There's quite a variation between instruments, and we'll see that in another measurement cycle. That's the same thing, but without the smoothing. And okay, so this blue line I'll use occasionally. That's the nominal most sensitive frequency for the ear. The ear sensitivity peaks around 3.8 kilohertz. And I find it fascinating that the violin has evolved to have a cluster of radiation resonances right around there. And particularly a number of really good violins, in my opinion, the N5 in the Paris experiment, the Vieuxtemps, another Guarneri, they have this great big peak there from vertical excitation. So all of us just say, if that peak shows up averaged over 4 instruments, that's significant, and it's several or about 2 dB high. So directly under the bridge, we gain a little in the bass, lose in the transition, gain a little in the upper hill. Okay, what happens if you put the post on the other side of the bridge? Now this question is almost like a joke question, or so it always seemed to me, but from Jim's model, he says there's not an obvious reason why it would make a difference if it was on the other side symmetrically placed. We wouldn't expect to see the same thing. But so we tried it here once, and it was quite interesting. So we did this experiment. So the red line is 2 millimeters north of the bridge, and the black line is 2 millimeters south. And I was, to my eye as a maker, I would certainly go for the red line here. This I don't know. The bridge hill, yes, and the upper hill, yes. It seemed like, in terms of what I'm looking for, better. I don't know the psychoacoustical effects of this, so that'll be one of the next experiments, and or one of the things worth looking at. So I thought that was very interesting indeed. It seems like a perfectly plausible place to put the Soundpost. That's the same thing without the smoothing. And again, you see this important peak here is jumping up. And so let's look at the individual violins. Okay, so Nick's violin here, I don't know, these are the makers. I don't know what the actual instrument was. You'll see it. We didn't see a shift here in the general frequency. There was a bit of a diminution in the amplitude. Alex is one big help to the Bridge Hill region. Otherwise, pretty much the same. And what we see quite a bit is an increase in C4 here. Here, for example. So a significant gain in bass in this case, and in the very highest, not losing anything in the Bridge Hill. A big change here, for better or worse. Now, when I see that the placement visually, it's more evenly placed frequency-wise between the other two clusters, so it's not obviously bad. Now, this instrument was very interesting because it had a quite suppressed B1 minus, which just jumped into focus. It could be, this is a single violin, it could be some little thing in the measurement that makes it an outlier, but it was interesting. But we do see the change here and quite a significant change in the upper hill. So in none of these cases, to my way of looking at it, is the instrument going to behave worse in terms of radiation. And in many of them, to my eyes, it says better. What we didn't measure on this is admittance, because if that changing in some, does it change in parallel or not? And as we'll see in the next experiment, that makes a difference. So we're not saying anything about admittance here. This is just radiation. So this is a deformation and arching you see in pretty much any instrument over time. The bridge forces, you know, what, 20 pounds pushing down there. It can't move here, so you gradually get this distortion. So why not put the bridge on the other side? It would gradually reverse the distortion. I kind of fantasize about having both positions marked out, and one could go back and forth over the years. Something I'm eager to explore. What happens if the post gets further from the bridge? So we have it 4 millimeters south of the bridge and 2 millimeters south, and not a big difference. We do see the energy moving from the B1 plus to B1 minus. It could help with wolf notes. B1 plus is often the major source of wolf notes, depending on what the, very much depending on what the admittance is doing. It seems to help the upper hill. So I would say tentatively that moving the post back from the bridge might help with wolf notes, and it might give a bigger output in the very high frequencies if you want it. About the same, or maybe a bit of loss in the others. And we see if we don't smooth it, it's quite significant because, you know, the wolf's going to happen at right at a peak, or at least an admittance peak. Okay, what happens when we move the post east towards the edge of the bridge? 3 posts were made from each of 4 violins fitted with equal tension.
Joseph, sorry, are you
Yes.
going on to the east-west already? Do you want to finish up the?
I'm sorry,
south?
absolutely.
Yeah.
Please, excuse me.
All
Let's you pipe in. I'll stop sharing.
Yeah. Let me swoop. All right, so that's where we were, right? You see my screen.
Yeah.
I'm also going to talk a little bit about the Post North-South project, taking somewhat of a different view at it. I'm sorry, I started from the incorrect slide. Oop, where is it now? I want to explain first what I'm going to show you, so you can make sense of that. Do you see my screen share right now with the?
No.
Am I sharing? Oh, sorry. I did.
Okay, here we go.
Yeah, you should see that. All right. So in what I'm showing you now, we're not going to look at the individual results. This is one trial run of something. This is too confusing. Let's take a broader view to get a different idea. Less detailed, but maybe easier to grasp and maybe conclude something from. So we already talked about these average bands here. So in the frequency range 200 to 780 Hertz, for example, we put an average band that gives us the average level in this frequency range. I'm just going to use that as a guide, basically. So here I've plotted the same thing, removing all of those complicated lines and just leaving those horizontal lines that give me the average decibel level in that frequency band. Just going to use each of those as a point. So for example, here the red line represents, let's say, Alex's instrument. I'm just going to take the value of the baseband here and plot a point, and do the same for all three other instruments, and then do this, in this case, for 4 people, and then each position. So in the example of the north-south project, 1 probably represents the very south position, then 2 represents the moving 2 millimeters north, 3 2 millimeters north again, 4, you get the picture. So as you read this plot in the lower left-hand corner from left to right, you get results that show you if I move from south to north, this is the change in this specific band, 200 to 780 Hertz. So it's a very, very broad view. It is maybe not the most useful result overall. We can do more detailed analysis that maybe tell us more different things, but as a first view, it is quite useful, especially when we're trying to answer the question, is there a trend that is common to all instruments here? And that question becomes important because in the beginning of the workshop, we talked about, okay, do you at home in your workshop have a general rule? Okay, I need to adjust the sound in this direction. I need to get more bass, for example. I will always move the Soundpost east, just an example. Or is it very specific to each instrument? Do I have to do different things on different instruments? That's, I think, a general question with all the sound adjustments. Are there general rules that we can apply blindly, basically, to every instrument? Or do we have to cater to every instrument individually? And if we see something similar to what we see here, so a general trend that is similar for all the instruments we measure, we might expect there to be a general rule that we can use in practice, which of course would be very useful to us. Okay, so I'm going to go a bit more into detail on what can we expect if we look at stuff like this. So the first one I already mentioned, there could be a clear trend. For example, all of them go down as I go north or something. All instruments do exactly the same thing. I can conclude there's a general trend, and I can use this for adjusting instruments. The other option, of course, the opposite is maybe it's random data, basically. All of them do different things. What can we conclude from that outcome? Either the signal that we are trying to detect is smaller than the error of our measurements. There will always be error in our measurements. And it could just be that there is something happening. We just cannot observe it with the tools that we have. The second option is that we are detecting some kind of signal, but it's just very different for each instrument. So for one instrument, if we want more bass, we need to move east, but maybe for another instrument, west would be better. That's the second possible outcome that we could have. In that case, we couldn't formulate general rules that are useful to us in adjusting instruments just in general, and we would have to accept, okay, for each individual instrument, I have to decide again which is the correct direction. Okay, now going into the post north-south project. Okay, so we used the radiation measurement. Joseph already introduced that. I first just added up all the differences in all the bands to show which band changed the most in general. So this is just adding up the difference from Alex's instrument in the signature mode region plus Andreas' instrument plus Nick's instrument, whatever. And we get the largest change certainly in the low frequency range as we move the post from south to north. It looks somewhat like this in the plot that I just introduced. So I have this little graphic down here that shows you this position, which is marked with 1, is representative of position far south. then 2 is our normal position, 3 is the weird directly under the bridge position, 4 is 2 millimeters north of the bridge, and 5 is 4 millimeters north of the bridge. We can maybe see a slight trend here for a rise in the lower frequency band. It is quite subtle for some of the instruments, and it is also not completely the same every time. So you see a dip in this dark blue curve at the under the bridge position, but generally there might be an upwards trend. Here I'm showing the same thing for all 4 of the bands, with the low frequency band being the most interesting and most useful, I guess, to us. I'm showing the same thing that Joseph just showed in more detail. The 780 to 1740 Hertz band is the transition hill, and there we see a dip at that 3 position, which is the directly under the bridge position. So for some reason, the transition hill kind of cares about being directly under the bridge with the Soundpost. The other bands, it doesn't stand out, that 3 position. Yeah. Okay, so the conclusion of this general overview might be a weak general trend might be detected in the bass response. So tentatively, we could think, okay, moving north might give slightly more bass for this group of instruments. The influence of the bridge foot is seen in the transition hill region, but not in the others. So for some reason that is important to the transition hill. I couldn't explain how or why. And then some adjustment of the bass response might be possible through this north-south movement. Very tentatively, not sure, but it's something to investigate more, probably. Okay, do you want to go into the next one, Joseph?
Sure. And let me just add to what Luca said. He's saying, not sure as a general rule, but there's enough variation among instruments that it may well be possible for your instrument. So don't rule things out because they don't follow a trend.
Basis, quite different.
Which kind of reinforces what we all know about getting down in the weeds and adjusting instruments. Okay, so what happens when we move the post east towards the edge of the violin? So you're moving it away from the center toward the sides of the violin. We made 3 posts for each of 4 violins, fitted with equal tension, as judged by the maker. We didn't have a quick way of doing it by measurements. So the first was 3 millimeters inside the edge of the foot, which is further in than I think most people would do. 1 millimeter inside the edge of the foot, which I think is about standard, and 1 millimeter outside the edge of the foot, which is a little further than some people might go. I've certainly not used to putting it out that far until we did this experiment. And we measured radiativity and admittance for this. So 3 millimeters inside to 1 millimeter. When we move it into the red, the more or less normal position, we see some gains in the bass, particularly B1 minus. And throughout these experiments, B1 minus is moving a fair amount. Not much change elsewise, a little advantage in the bridge hill. So it says, and then a little drop in the upper hill. Now, if we go, let me just see. I think I've got that. Excuse me, I think I've got the slides wrong. Let me go straight to this one. So the green is the 1 millimeter on the outside. The red is the normal. The black is the further inside. And we see the green, if you're looking for strength in the bridge hill region and in the bass, it seems to work well all over. There aren't losses. So what happens if we go further still? I imagine it wouldn't be continual improvement if you think of that in an improvement, but this certainly read my sense of where the norms are or where they could be, what's possible. And I readily explore moving it outside the bridge now. I know plenty of makers probably do already. I was talking to Sam Zygmuntovich, and he certainly does. Now, let's look at admittance. We saw how the radiativity changed. Admittance, we don't tend to see a lot of action at A0. But what we see is, as we go towards the outside, the admittance is dropping, generally speaking. So the black's on top in all bands, and the green is at the bottom. So the furthest out here, about equal here, and somewhere in the middle there. Why does that matter? Well, I've just normalized the admittance and radiativity, overlaid them on top of each other, and it's very interesting. If the admittance is low and the radiativity is high, the extreme case being A0, that's what the acoustic efficiency is very high. In other words, you're not, for very little motion, you're getting a lot of output. And we see that that generally speaking, these low frequencies are pretty efficient. Terribly inefficient around the bridge area here. I don't know what causes that, but it kind of explains, there's sort of typically a dip here in radiativity, and it gets, you get closer up here. So what we see here is the radiativity highest and the admittance lowest, right around there where the wolves happen. So that it's the wolves respond to the admittance, not the radiativity. So if you can get that sort of effect, you're likely to be able to help with a wolf note. And this pretty much happened across the instruments. I won't show the individual ones. So this does suggest a reasonably robust strategy for dealing with wolf notes. You know, pull it out towards the edge of the instrument a bit more. It would be nice to do a study based, you know, looking out at these from the wolf note's point of view, because a wolf note subjectively is very easy to identify, whereas other quality parameters are more difficult. Luca, do you want to pitch in here?
Yeah, I'm gonna go over the project also. Okay. So again, this is going to be somewhat of the broader view of the post-West-East project, mostly looking at from the perspective, can we find rules, general rules that work for all of the instruments that we looked at in the project. Right. I use the radiation measurement again. And again, I plot this cumulative change and saw the highest, largest differences in the treble hill this time. This is the general plot for the 4 instruments that we have. So on the left, you have the west position. In the middle, you have the normal position. And then on the right, you have the outside or the east position. This is for the low frequency band. And we can see a slight trend upwards for 3 of the 4 instruments. And then just a slight kink in the trend for this light blue line here. Looking at all of the bands, it is much harder to find trends. So for example, in the transition hill here, 2 of them generally go down, 2 of them generally go up. That's not a general trend, but there's some disagreement, I guess, between the instruments. In general, where there might be a trend is again the low frequency band. The other ones are more random. For the bass response, as I said, there's a general trend, and it increases with moves to the east. So the rule maybe that we could try to find from this would be move it east to get more bass. This works with the other project that we did that does east-west movements that we're going to get into later. So while the data that I just showed is a very weak trend, we add another experiment to it which supports it. So this west-east was one of the more interesting ones to me, where there seems to be somewhat of a general rule to it. Okay, I have the admittance measurements for this project in here as well. We did for some of the projects, we do admittance measurements, and I just put them in for the ones where I had something interesting to say about it. Here the changes were relatively large in 3 of the 4 bands, everything except the transition hill. which is interesting as it's contrasting the radiation measurement quite clearly. And if we look at the baseband or the signature mode region, we get basically the opposite trend of what we saw in radiation. So while the admittance goes down, the radiation goes up. So it might hint at, okay, the efficiency of radiation is actually increased. Again, while we see big changes in all the other three bands, except for the transition, excuse me, as well, there's just no trend. It's more random, quite interesting on an individual instrument level, I think, but I'm trying to find rules here, right? So we can ignore the three upper bands and just focus on the bass band for the results here. Okay, so the conclusion would be a similar but opposite general trend for bass response is visible in the admittance and the radiation. So as the radiation goes up, the admittance goes down, and generally moves to the east, increase the bass response. And I write here, it agrees with the other project that we're going to introduce later. In general, this seems okay. I can tune maybe the radiation efficiency by moving east, which is quite interesting. Okay.
Good. Yeah, let me add to that, unlike some of the results we're finding where I have no idea why it would be the case, this seems to make sense. Imagine the posts were put right in the center of the instrument. The bridge would be moving a lot. It'd be rocking over the posts with very little resistance. But it wouldn't radiate very much at low frequencies because it's, cancel itself out. And the whole point of having the post asymmetrical is to introduce this acoustical asymmetry. But as soon as you start moving the post away, it's harder for the bridge to move. So I think, Jim can pipe in later if I've got that wrong, but that does seem to make sense to me. The question is always, how far can you take it? When you start moving much past the edge of the post, well, there's the F hole, the upper hole of the F hole, and the flexibility introduced in that area by the F hole itself. We'd probably start to see things change quite drastically if we took it out further, but that would be worth trying in another experiment. Okay, let me share again. Okay, Soundpost length. What happens when we make the post long? 3 posts were made for each of 3 violins. The position was kept constant. There is a normal length. There is one 0.3 millimeters shorter and 0.3 millimeters longer. And we did a smaller radiativity, just 7 positions around rather than the full 12, we just wanted to get a sense of what was going on. And so these are, I think, very normal adjustments one might make. Okay, normal plus 0.3. We seem to have a gain in those 2 regions, in the transition hill and in the bridge hill. So I'm all for that. But now let's go the other direction. This baffles me. So this is a loose post, but we seem to have a still bigger gain. So averaged over the 4 violins, the loose posts seems to give more output across the board. I have no idea why that would be the case. It suggests, if this is indicative, then maybe we shouldn't be. Maybe we should be having our posts a little looser, but I don't understand this. So that's all 3 of them together. And again, the loose post seems to do as well as any of the others, plus a little more in the very high. It's interesting too that the frequency of the B1 minus seems to go up a tad, as well as the peak height. Crooked Soundpost. So we're constantly adjusting by moving one end of the post, either out of convenience or out of, with a plan. So what's going on there? So each of 4 violins was fitted with a single post in a kind of normal standard position. So the top, we did a measurement with the top and bottom in normal position, and the top was moved 2 millimeters west, which would be toward the outside of the instrument, and then 2 millimeters toward the inside of the instrument. And then we did the same thing with the bottom of the post. And we measured admittance. I'm not going to show admittance here because I didn't have a complete set. But so we'll look at the radiation. So what are we seeing here? The black line is a normal position. The east, when we go in, that we get the red, it seems to give more bass. A little more in the transition hill and a little more in the little less in the upper hill, but it's quite interesting. We get a higher peak here, but a lower overall level. Now, when we do the back, okay, first of all, we should say these aren't drastic changes. Oops. The back, we see a similar range. Not much to look at here. The normal seemed to work better, maybe. Certainly in this area. That's all I have to say about that one. I haven't spent a lot of time with it, but Luca, perhaps you could fill us in.
Yeah, I'm going to go into the Cricket Soundpost project as it relates to the east-west. They are similar, right? In both cases, we're moving something in this direction. Just in one case, just on one of the plates, and the other one on both. Okay, you should see that, right? So the Cricket Soundpost project. Again, I'm going to give a general view using the radiation measurement first, or the HV, both directions radiation measurement. The largest changes were in the signature mode region and in the bridge hill region, overall these instruments. And this is plotting the same as we did before for the signature mode region over the 4 instruments. And this was quite interesting to me, so I've put little indicators here. This is in the order that we did the measurements, which was move the Soundpost west on the top plate, then east on the top plate, then west on the back plate, then east on the back plate. And we do see a trend that is quite similar over these instruments to my mind. So the orange line maybe is the most representative. We move east on the top plate, and the signature mode band goes down in amplitude. Then we move east on the top plate. Sorry, I think I just misspoke. It was west on the top plate for the first step. Then east, we get an increase. Then we move west on the back plate and we get a decrease. And then east on the back plate and we get a slight increase in this case. This kind of mustache-shaped pattern, or whatever you want to call it, this down, up, is repeated somewhat in most of these instruments. Again, looking at all of the bands, it is harder to say something about the others, as we saw before. So in the bridge hill, we saw a lot of change, but it is not very systematic or similar between the instruments. So we can't conclude a general rule, I think, from that. So we could conclude, okay, the bass response and bridge hill, they show largest changes, that's clear. And there's a somewhat similar trend between the instruments for the bass response, but it's not very clear. With an HV radiation measurements, we're including the horizontal and the vertical excitation. And I thought, okay, there's a trend here. Maybe it's stronger in one of those individually. I looked at that and I found, yes, it's a bit stronger in the vertical excitation radiation measurement, which is to be explained, I think. Here, almost all of the changes in the signature mode region, and the same pattern as before looks like this, which to me is quite a clear result, which I was surprised by. So the same up, down pattern is repeated pretty much for all of the instruments. So for west moves, we get a decrease in the low frequency band, and for east moves, we get an increase. Okay, so concluding from this, mostly bass response and bridge hill are affected in general. For the bass response, we get somewhat of a trend that is common to the instruments that we measured, which is only 4, of course. We should keep that in mind, but if it agrees for 4, it might agree for 10, maybe next time. And in general, east adjustment increased bass response and west adjustments decreased the bass response, regardless of top or back plate. So it didn't really matter for that on which plate you were moving. In general, I find it encouraging, I guess, that this seems to agree with the east-west experiment that we did. So where we kept it straight but moved it east-west. It seems to be the same kind of trend. Repeating it twice makes me trust it a bit more. So yeah, there might be something here. As always, more research is needed.
All right, that concludes the formal part, I think. Any other? So let's open it to questions related to these projects. Anyone have a question?
Can I chip in for a question of fact?
Please.
You presumably for the tilted post experiments, you were using a regular post, not one with your plastic tilting ends, or did it still have the tilting ends?
I honestly don't know, but Alex?
I'm pretty sure it was normal Soundpost.
Yeah,
I couldn't swear on it, but yes, I think it was normal Soundpost.
Because in my book, that would make a difference. So it's
indeed, yeah.
Yeah.
I apologize for not having a quick answer. Is Alex Curran here? He would know, but we'll get back to you on that. And well, I should say that this is a sort of a follow-up on Jim's work, and people who are interested should in the Soundpost should see that the talk he did last month, which is now posted on more the theoretical side, that drew a lot of stimulating conversation. Other questions?
There are also questions in the chat. There's especially one that relates to what we were just talking about. So David asks that if the swivel of the Soundpost adjusts, then with Jim's model, we expect a quite big effect of that, or that we're removing an effect of tilting a Soundpost. And yeah, I think, David, your understanding is correct. In theory, that should make a big difference because we can tilt the Soundpost without affecting basically the contact point on the plate.
Colin? We can't hear you.
Audio on. Can you hear me now?
Yes, indeed.
Okay, fine. When I did the finite element analysis of what happens with the Soundpost position, I found a huge amount of difference, for example, between having the Soundpost, as you might expect, in the middle of the violin rather than under the feet.
Mm-hmm.
Now, did you ever try putting the Soundpost in an extreme position? And because if you see what happens at an extreme position, it's much easier to then work out what happens when you come to the optimum position.
The short answer for me, no. I've measured, of course, without Soundposts, and you see a difference. I don't know that extreme to the range we're working in. I don't know whether there's any kind of certainly not a monotonic progression. I mean, when you're in certain areas, certain parts of the structure are engaged. If you move to the center, for example, that's so drastically different. I'm not sure it'll shed much light, except to do with the admittance and radiativity.
Well,
I think that's a very good example.
I think it would look that. I mean, we know because the whole going back to Schelling and Kramer and people. I mean, the importance of having an offset Soundpost, that it allows you to couple the transverse bowing motion into an up and down motion, which is the breathing motion, which radiates the sound. It's particularly important, as comes out in what you'll be talking about now, in the signature mode region. You expect that, but so it would certainly be interesting to know what actually happens as you take it out from the center and go out towards the treble side foot, because undoubtedly, empirically, violin makers have worked out that that's a very good position to put the Soundpost in. And it would be interesting to see, what happens beyond that to show that it really is an optimum position. And
Um,
because the whole basis of understanding what the Soundpost is doing is to, as you correctly said, is to introduce that asymmetry, which allows the coupling of the anti-symmetric modes with the symmetric modes, without which you won't get so much sound, particularly at the lower frequencies.
Oh, thank you for clarifying. I agree completely. Whether, practically speaking, mounting that experiment would be it'd be a lot of work. So it may not happen. But Jim, tell me, did George Stepani do some things with that? I know he did quite a thorough investigation with early instruments and center soundposts, and indeed he found a huge wolf.
Yeah, I can't remember if he ever did one in the center. As you said, an instrument without a post. Well, I have done some measurements on viols where some of them don't have posts, and then the later ones do have posts. And certainly you get a very striking effect there. I only did admittance at the time, but one of my theories for what the post might have done back in the viol era, maybe players were gradually getting more adventurous and playing further up the fingerboard. If you have a viol without a post, you get the worst of all worlds, because you have a whopping resonance that gives a wolf note without making any noise, because it's more or less cancels the radiation. And as soon as you put an asymmetric post in, you lose that effect. You tame the wolf in the way that you've shown, only more drastically. So I do wonder if that was one of the things that persuaded people that a post was a good thing. That say the invention of the post predates the invention of the violin, I think.
Well, I think it's here to stay. Any other questions? We must have done a remarkably good job in it.
Jeffrey has a question.
Okay.
This is a bit off topic, but the discussion about viols without a post just raised it in my mind, which is that when you see lots of paintings and drawings of really early stringed instruments, you often see the bridge way down towards the tailpiece. Does anyone have any comments about that?
I've certainly heard George Stepani talking about it, because he did maybe it was a talk here, maybe it was somewhere else. He did a survey exactly of the kind of artwork you were looking at. And I think, yeah, viol players are more given to trying drastic experiments. So I'm sure someone has told me about having a class with some leading virtuoso who didn't like their viol and moved the bridge all the way down to bottom below the holes. They're not F holes in that case.
You have seen those kinds of paintings and drawings I'm referring to.
Yeah,
right?
yeah. I've certainly say George Stepani has made a lot of that. He would have known the answer to that question. One of the many ways that we miss him.
So I'll add a little George to this. He was saying, looking at pictures, if you have a picture that is a portrait of the person who's been painted as opposed to cherubs and other things, that those instruments and those artifacts that are on the tables are very important to that patron. And so you can pretty be assured that wherever that bridge is on the royal or rich person's portrait is what it was. If you've got angels in the corners, maybe not so much.
And there's one hypothesis I once heard also, that so in those days, maybe you would go to a different place, a different city, and they would have a different tuning. So you would have to adjust to their tuning. And someone said maybe they just moved their bridge to achieve that change in tuning. Makes some form of sense to me. I don't know. I don't think we have proof that that's what they did, but it's interesting.
They'd have to move their frets as well, of course.
Yeah, if it's an fretted instrument,
frets.
of course. Just on violins, that would work. Yeah. We have also questions in the chat that we should answer, I think.
Yeah.
So Bill asks, for example, if we repeated all the experiments where we changed location to provide a repeated measurement that proves that more. We did that in the previous, so the week before we did the actual workshop, we tried basically everything that we did at the workshop on Joseph's instruments on a single instrument, and then repeated that a few times to find that we can actually repeat the result at the workshop. That's not really practical to repeat it with 5 people 5 times or something. We just don't have the time. So the repetition that we did is basically having multiple people do it. If they get the same result, we're calling that a repetition result. Of course, it would be better to repeat each individual result, but we just can't do that in every case.
So yeah, looking at the chat, we have right at the beginning, David Pulitzer. So the swivel adjusts to the angle of the surface. I thought Jim Woodhouse emphasized that the nature of the contact is crucial. Yes, well, this eliminates the Woodhouse effect, where changing the fit will essentially change the position. And so if it's important to be able to get the Woodhouse effect, then you don't want a swivel post. For me, the main thing about the contact is that it doesn't introduce spring. And as Jim showed, when you've got poor contact, you've got kind of a springier surface, or a more springy surface. I'm fairly convinced that the adjustable post is, if you switch it back and forth. Did we do that? Did we switch back and forth with traditional posts? I mean, I don't think we get any differences outside of measurement error. Tom Crowan, in your north, south, and east-west experiments, how did you control for changes in tension? We left it to player judgment. That's probably not ideal, but we're hoping it averages out across the experiments. We couldn't, it's quite difficult otherwise you'd have to sort of mic the outside of the instruments and a lot of things. So it's good. We did it as well as we could. The Anders Anders is saying for hard dankers, which have thicker plates, not unusual position Soundpost as far as south as 10 millimeters. That's interesting. The experience is that this does have a perceivable effect on the sound, somewhat softer maybe. Okay. Oh, we got some hands up. Colin?
How do we put the hands up?
You go to the thing on the bottom that says react. What?
Okay.
Okay. My question is one of the measurements themselves, which are obviously fine. When Joseph was talking about his measurements, you referred to radiativity. And were you measuring that externally using your averaging, or was whereas when Luca was showing his pictures, at any rate, it was a microphone that was very close to the bridge.
No, that was no. In all cases, the microphone distance was the same, 20 centimeters from the center of the instrument. The photographs can give the impression. What we did change is.
So you didn't measure around the plane. It was just a position.
No. So let me be clear. The ones that are marked as HV24 means 12 positions horizontally and 12 vertically. Some of them for speed, we just did 7 in front, horizontal and vertical, which gives a pretty good approximation.
Okay, thank you. It's just clarification.
Hans? You need your sound on.
Yeah. Does anyone remember? I mean, I found this in England in the late 70s. It's a Soundpost with a swiveling plastic end, and then you can lengthen it and shorten it via. Hang on, let me see if you see that.
You put washers in, yeah, absolutely.
Oh, you put washers in.
You can, or you can adjust the
Ah.
length. No, yes, that post came out a long time ago. I bought one, and I always thought it was a wonderful idea. And it was, I think, the father of all these ones that have come out. But when I finally got around to trying to use it, it had dropped off the face of the map. The person had a patent on it. Obviously, spent a good deal of money doing it. It was sort of heartbreaking. It was beautifully done, ingenious, but like so many things, it falls by the wayside. Now, of course, with 3D printing, it's so much quicker. You don't to make these things.
I remember people objecting to it because there's a plastic swivel end. That's basically,
Well, people object because something's different, and it's always good to be
Yes.
skeptical. But it's been. I hope now that nobody is particularly shy of it as a concept. I mean, I don't think there's any reason not to use it. One thing about models like the one you're showing, where the swivel point is several millimeters below the surface of the post, is if you can imagine that in the top of the back, if your swivel's here and you move the post sideways, the length goes down a little, which makes it a little unstable. So what we did, and it was Alex Curran's idea, we were trying all sorts of things, is we have our swivel joint, so the contact with the flat surface has basically half a sphere behind it, and it can rotate, and so the length doesn't change at all. And so I think for stability, that's a good approach. So it's a nice refinement. But yes, I owe that Soundpost a debt of gratitude. Do
you remember what it was called?
No, it was something very modest, and
no, okay.
I don't. I'm afraid. I have to say, I tried many times finding the person, but there was nothing around. So Anders?
Yeah, it's a bit off topic, but I should have asked Jim the last time if the bending stiffness of the top around the soundpost and the bridge is included in the model.
In the model, yes. It depends what you mean, as is often the answer to that kind of question.
Because you were talking about the contact stiffness, and there should be a serial between the contact stiffness spring and the bending stiffness spring, sort of.
Yeah, if you're really talking about bending and rotation, then that affects the torsional contact stiffness, and that didn't seem to be very important. There is a spring in the normal direction, but that's a more global property of the plates, because it's how freely they move apart and together at the post position, which is not just local bending stiffness, but is somehow, depends on the modes of vibration in the near each frequency. So it's rather a complicated thing.
Okay, thank you.
But the cigar box model had everything in, but mainly one of my conclusions was that the torsional stiffness didn't matter, and that goes with Joseph's experiment with the thinning down the middle, because we did have some discussion after the talk. Someone else was remembering, and
but I'm talking about the top plate and maybe the back plate, not the bending stiffness or the torsional stiffness of the soundpost.
Yeah, but that's the mechanism. If rotation of the plates near the post ends has any influence, it has it through the torsional contact spring.
Okay.
And if it doesn't have an effect, then it doesn't have an effect. Doesn't really matter what you do.
Okay. Even if you put the soundpost very far south?
Well, I didn't try that, but it seemed to be that the normal stiffness was important and the bending stiffness was not important, so far as I found in that particular study.
Okay.
Let me put my hand back up again.
Jim, please.
Yeah, I just wanted to ask an entirely different kind of question. I mean, this was a really interesting presentation. My sense is, I just wonder if you agree with this, that this whole experiment, what you did at the not Oberlin meeting this year, you reached some conclusions which say something about workshop practice, maybe even more than the bridge study did. If anything, you've got some surprisingly clear trends or not trends here. I mean, were you pleased with the whole thing? Do you feel it's given you something as a maker that gives you new tools and maybe new questions to ask?
I certainly was delighted by everything about the workshop. But the results, yes. I've actually changing where I mark out my Soundpost now as a default position. And I'm just about to call a person who had a problem with wolves and say, send it to me again. I have an idea now. I'd always treated the Soundpost as relatively random. I mean, just move around in circles and watch the player's expression. Not because I believed it, but there was nothing around that convinced me otherwise. But this says, no, it's not quite random. There's a lot of variability, but there are some things we can really consider when we're setting about doing setup, and particularly the east-west. And for me, I'm not afraid of doing something outlandish for a bit. Putting them on the other side of the bridge, I want to start doing that and feeling that out. Luca, what do you think?
Yeah, I agree. In like that W shape that I showed, which showed me, okay, the east-west movement is really, we're seeing something for all of these instruments. This is quite interesting. When I saw that trend first, I was really excited because I was very skeptical in the beginning. I will admit at the start we are asking, are there general questions? And my opinion was really, I can't believe that there are general things. I think violins are so different. But that was somewhat short-sighted, I think, because as we explained, the East-West has a lot of merit working just in the general principle of a violin and not interacting with specifics of a specific violin, but the general style of how does a violin transform the string vibration into radiated sound works well with what we observe. So it changes completely how I view adjusting sound on a specific instrument through the Soundpost, because before I would say, okay, I just have to try it. I don't know what to expect from this instrument. But it seems to me now that there are certainly general things that we can use.
Yeah, especially in the low frequencies. I mean, that makes perfect sense, doesn't it? That the place you got something looking like systematic trends in more than one of your plots was particularly in that signature mode band. And of course, that's the only region where the vibration properties of all violins are somewhat similar. Once you get out of the signature mode region, all those peaks in detail are all over the place. There are elements of consistent stuff, but the individual modes, it doesn't make much sense to try to track. But up to 600, 800 hertz, that in that region, all violins are rather similar. The variations are relatively subtle. And so it makes perfect sense that something like moving the post would have an effect which is reasonably consistent across instruments. So all of that makes me think that you've got real data here.
Thank you. I used to think of the Soundpost length as especially important, but now seeing the results, I mean, of course it's important, but it doesn't seem to be the most striking result at all.
But there were some questions in the chat about that as well. And I was thinking, should I show the slide that we had in the very beginning that I did at your workshop, which is, I think, even clearer showing what the Soundpost Length does and doesn't do. In Joseph's workshop, we had the Anima Nova adjustable Soundpost, which just has a thread inside of it. So you can just, without taking anything out, taking the setup off or anything, you just adjust the length. So it's a very, very clean experiment that we were able to do and repeat a few times. Give me a second to share that slide. And I hope I don't disappoint anyone, but these measurements, well, they show roughly this, which is 4 different Soundpost lengths. And at the top I've put, we used the original Soundpost length, and then went 0.36 millimeters shorter than that and up to 0.71 millimeters longer than that, which is the range that we were comfortable with. But much more than that, we didn't want to try. And these lines are basically on top of each other. This is very much the measurement error. There's nothing that we measured here.
I'd forgotten that. And yet, Claudia's group found that, I think Bill Favard found that players can subjectively detect a change of, what was it, some
I think
20th of a millimeter
was the threshold. Maybe 0.15.
Yeah, it was under that. Well, I think players were a little under, listeners were around that. Yeah. So what's happening in between? I mean, this to me is a puzzle and needs more.
Yeah, to me, one reasonable explanation would be that it's not in the physical function of the instrument as it radiates sound, which we're measuring with this radiation measurement, but it's more so in the playability maybe. So what Lai Fu, Claudia's student, did is have an actual playing session where a player played an instrument after adjusting the Soundpost length. Maybe they played differently. Maybe the input is quite different. In these measurements, the input is always, it doesn't care about the Soundpost length. It's always the same. It's an impact hammer. But maybe the input changed because the player felt something in the feedback from the instrument. That could be a reasonable explanation to me.
Also, that must be that the admittance is changing. Did we do the experiment with admittance as well, or did she?
I don't remember now.
Because that would then be well worth doing, because if it's more sensitive to admittance, if admittance is more sensitive, which seems broadly true, that could be interesting. Unfortunately, we don't know yet to what extent players feel admittance except around wolf notes. It's not an easy one to study because there's not a simple knob for admittance. Maybe with an electric violin or some sort of a setup, that would be very interesting because it would relate the sort of work Jim has done over the years with admittance and playability with the psychoacoustics of playability, which is somewhat different. Hans, you've had your hand up for a while.
I was just wondering if you would involve the musician in actually looking at the graphs and looking at the data, whether that would have any positive influence, or it might be a total nightmare.
Well, I mean, how do you mean? Show them the FRFs and ask?
Yes, show them the FRFs and see if there's a psychological connection to what you're seeing on the screen as we are doing, because we're not linking it directly to the player's experience.
Well,
could be a total nightmare.
Right.
That's an interesting question. I'm just trying to think how one could focus that into an experiment.
Yeah. So I've done some of that today. So I'm at the violin making school in Brienz right now, and we did some bridge experiments. We had different bridges on different instruments. We took measurements, we played them in blind conditions, and then wrote down what do we think about it, and talked with musicians about, okay, does all of this make sense to you? You're hearing something, you get a graph that shows you what you are supposed to be hearing, I guess. Does it relate well to each other? And today it turned out yes. So today we had stiff and not so stiff bridges. The stiffer bridges give more high frequency output in the measurement. And the musician said, oh, this sound is more sharp, I think was the word that they used. Today it worked. Most days it doesn't work. It's most of the time it's much more complicated than that. But from my experience, if you get the right musician who is interested in that stuff, they see it as, yes, this is a database, is something that I can use to understand what I'm hearing and the connection to the instrument. Some people don't relate to that. That's fine also.
Something else on Hans's question. There is another aspect of this, isn't there? And it depends exactly what he was asking. But if you're thinking you've got the musician there in the shop while you do post adjustments or whatever, and you're looking at the measurements, if you're there as the maker saying, oh, look at that, that looks exciting, that should give you more high, then many suggestible players will immediately, oh yeah, that's much better. I mean, and that would go with all sorts of folklore of people doing non-adjustments and players but stating with confidence that they've made an effect, and people can and immediately hear it and will be prepared to pay for it.
Yeah, that's a huge effect. And so, for example, in cases like today, I always let them listen first and then show some data, which is always a trouble. For example, at the workshop as well, we want to introduce people to what we're doing. For that, we need to show data, but then we're kind of prepping them for expecting the results that we already have in front of us.
Yeah. Andreas?
Hi. 2 points. First, to the length of the Soundpost. Very interesting that, Luca, your graph didn't seem to show any difference with quite significant Soundpost length, which goes completely against all my experience. It also goes against the the experience with the carbon posts that I don't usually use, but I've got a little bit of experience, and colleagues obviously do, where the post stays in the same position and it fits because it swivels, and you do all the adjustment with the length. And it very clearly has got an effect on the sound. We touched upon it. On your graph, was that radiation where we didn't see any change?
Yeah, that's radiation.
You didn't by any chance also measure admittance?
I don't think so, but I would need to look it up right now.
Okay.
But that would be definitely the next step, I think. If I don't have the data, we should get that data next and see if there's something there.
Well, exactly. I think that would be really interesting because, I mean, the graph was very interesting, but it still contradicts completely workshop experience, and somehow somewhere we need to get them together. I'm not certainly not believing, you know, what I experience just because I'm seeing a graph. But I'd love to marry them up somewhere.
Yeah, right. And that is, I think, the important step where we have to say, what is this graph saying? This graph is saying that the radiation measurement result is not affected by Soundpost length in that measurement. Is that saying that playing an instrument with an adjusted Soundpost length certainly doesn't care about the Soundpost length? No, it doesn't. Because in the playing situation, we have a player interacting with an instrument. In the measurement, we just have a hammer hitting it. There are many factors that go into it that might be affected by the Soundpost length that the radiation measurement doesn't care about, I guess.
And sorry, I'd be surprised. I mean, granted that radiation and admittance don't track each other. If there's so little change in radiation, I'd be shocked to see a large change in admittance, especially from such small things structurally. Jim, can you think of any model for this that would?
It's not off the top of my head, but I wouldn't attach any significance to that. But just to follow up Andreas's point, in a more crude way, Bernard Richardson, who some of you may know, he's more in the guitar acoustics world, but he taught a course on musical acoustics for many years. Something he had as a lecture demonstration instrument was that he took a probably not very valuable violin, drilled a hole in the back and put a brass bushing in at the post position. Then he had a post that could be screwed in from the back. So a player could play it and adjust the tightness on the screw, and the in the context of a not very good instrument, needless to say. But he reports that there were significant changes and players had no difficulty at all choosing the tightness that they most liked. So there is something to follow up here.
Yeah, well, when there's such a big gap between the way we measure and what experience, I mean, it does really, it's kind of exciting. It's
Yeah,
something to be discovered.
absolutely. I mean, your measurement, the most convincing kind of measurement is one that shows a null result. Because something has to be right to have no change at all. If you do see a change, you're never really sure whether it's caused by the thing you thought you were changing or by something else that you didn't mean to change but was going on in the background. But if you get a null result, it's hard to fake that.
Yeah, that's an interesting point. Now, I wonder, did maybe you know, Luca, when they were doing these tiny changes, is it the case they were recording the player and they could also tell from the recordings?
And
I think
so the experiment itself was live. Maybe it was also recorded, but the results that they reported on, I think, were from a live listening test. Maybe those recordings exist as well. I don't know that.
I thought I remember reading that it also showed up in the recordings. Okay, Anders, you've had your hand up a while.
Yeah, I was wondering, how long did you wait between the changes to the Soundpost length?
I saw your message in the chat. So the experiment that I showed that showed a null result, that was just right after another.
Yeah.
It was maybe take it out of the rig, take it to workbench, adjust the length, bring it back. Maybe a minute between, maybe two, something like that.
Then I wonder, do the instruments find their equilibrium within a few minutes, or does it change over time, over 24 hours or 48 hours, or if you have the same humidity level in the air, of course?
Well, that's a big question. The study of the deformation of the canone, where they took it out, measured it very accurately, and someone play it for a few days. I mean, it was being loaned and then put it back, and how long it took to get back to equilibrium. It was in a matter of days. Now, of course, if you have a Soundpost inside, if you're not taking it out, as was the case with the carbon fiber one, that takes that out of the question. But I wouldn't think, I mean, from what I've studied of the deformation changes, I think the recovery would be very quick for small things like that. But maybe someone else has better instincts about that.
I think it would just be interesting to research.
The counter argument, I mean, there is a much slower effect, of course, which is familiar to you all, which is that if you have the New York style of super tight post and you wait for a bit and the arching distorts, and so you take it back to your New York adjuster and they fit an even longer post. That's not a matter of hours or days. That's taking a little bit of time, but accumulates into the distortion that you all know and love.
Indeed. All right. Are we about out of questions? Let me just check the chat site.
There's an interesting question by John, who asks if moving the bridge, for example, a millimeter west, let's say, is similar to moving the post a millimeter east. So you're changing the relative position of a bridge and Soundpost. And that's something we've thought about in the past as well. I'm not sure that it's exactly the same, but you're saying you use it as a first estimate. Like you just want to know what will this effect roughly be like before adjusting a Soundpost, just move the bridge a little bit. We did some listening in Vilfava with moving bridges. It was really hard to track something down in a similar way to that. It's really hard to track something down with a Soundpost. So to my mind, it could be a similar effect. But I don't have good data to support that thought.
My sense is that north-south, it might be reasonable because if you measure like from the violin body, which we did a lot a year or so ago, and the exact position of the bridge on the body is very important. I mean, and it's more sensitive east to west, presumably because the grain's going north-south, so it's much stiffer in that direction. So I don't think it would be a very good prediction east-west. It might be north-south. But now I'm kind of throwing out all my old rules of thumb because I think a lot of these effects are quite independent of each other. Who knows? Who knows? Alcus?
Yeah, I just wonder, to Andreas' point on the length, the effect of the length of the post, presumably in the same exact position, but change the length, that players have a preference versus what you see in the spectrum, what you concluded earlier. I just wonder if you have different players and different bows, if the effect of that admittance, the length of the post, will different players will have different preferences.
They will, yes. I think that wasn't that Claudia's. It's all been written up in the paper, and you could certainly you'd enjoy it. But my memory is that there was variations from player to player, and they were quite. I think they could reproduce their. It was quite reproducible, but all this was again in a very fine range.
So, Joe, I'll take that the admittance refers to playability. Some players will call it playability. The response to the bow pressure force.
Well, it depends how you define playability. Jim defines it in a very specific way as the ease with which you can get the Helmholtz motion started, something like that. Right. But for players, playability is a constellation of effects, how even it is from note to note. There's all sorts of things going on. And so I think, well, we need a more study of all the different effects so that can affect, that a player would describe as a playability effect. And I think that a huge part of it is the, well, actually, I'll stop right there. I don't have a good sense of what it is.
Okay. It makes sense. Thank you. Thanks.
Jeffrey?
I can tell you that in New York, when Rene Morel was active around, I guess this is the 70s and 80s, that violinists who are always looking to get, to really crank up their instruments, in general, the trend was longer posts farther out, which would kind of go along with more aggressive playing. That's what people seem to want, and that's what he gave them a lot in his adjustments.
But I think here we're seeing a confirmation of his the correctness of his intuition, of his practice in terms of moving it out. I think that in the ones in the tests, and certainly ones I've been experimenting with, I think any player would like it better with less wolf, more bass, and a bunch of other things. The tighter post is a different question. My sense is that I don't know. It was that instruments that had too flexible tops seemed to benefit by tightening them, but I'm not confident about that anymore.
There's just, it's so many variables. It just seems like a giant wading into a giant swamp all the time.
Yes, exactly. But it's an enjoyable swamp to poke around in. All right, shall we throw it into the general discussion mode?
If that's where we're going, let's just thank Luca and Joseph for this really interesting presentation. That was, thank you very much.
You're welcome.
Thank you all, and a big thank you to the makers who who sat there and did all these adjustments day after day, and to Luca and Lonnie and Alex for measuring, and Alex Curran was kind of running the making side. So it's just a great example of teamwork and very enjoyable. So thank you all. And let's continue this trend. Last year we did bass bar, or the last time bass bar, and I think again that showed some information that I find very useful in the workshop. So I'd love for these acoustical meetings to be continuing this. I think we're now in an area or at a time when we can usefully explore these questions, which have more direct relevance than the kind of foundational acoustics that, you know, Weinreich and Woodhouse have been doing, which explain how things work in general. So it's an exciting time, I think. So all of you